Namaskar and welcome to this lecture in our series of concrete engineering and technology. Continuing our discussion on special concretes, where we were talking about high workability concretes in the last class, we had developed the following ideas. Concrete, mortar and paste all can be modeled as a composite having a fluid phase with particles suspended in them. Paste can be modeled as cement particles suspended in water, mortar can be modeled as sand particles suspended in paste, and concrete can be modeled as coarse aggregate suspended in mortar. The properties of the composite, whether it is paste or it is mortar or it is concrete, can be determined by the properties of these two phases. That is, in the case of concrete, for example, it will be the properties of the aggregate and the mortar, and also the volume concentration of the particles. That is, if you are talking of concrete, how much coarse aggregate is there in the composite by volume. We had also talked about the problems of segregation and particle interlock in the context of the carrying capacity of the fluid, the conditions of flow, and so on. We have talked about the properties of the fluid phase, which can be modified by changing the concentration of particles therein, and superplasticizers help us directly in that context, and also using viscosity modifiers. We had also built an argument for having a reduced volume of coarse aggregates in high flowability concretes. In fact, there was a slide, if you would remember, where we had said that depending on the concentration of reinforcement or the complexity of the shape in which the concrete has to be cast, the maximum volume of coarse aggregate in the concrete can be limited or needs to be limited. Continuing with that discussion and reiterating that paste is water and cement, mortar is paste and fine aggregate, concrete being mortar and coarse aggregate, and the suspensions as we have discussed. We now talk about self compactability of concrete, where we said that on the one hand we need increased deformability of the paste, which calls for an increase in the water to powder ratio and the use of superplasticizers, and on the other hand we require adequate viscosity, and for that we need to reduce the water powder ratio and we use viscosity agents. So, these two are the chemical admixture route, or this is the physical route where we are trying to change the water powder concentration in the system. Now, as far as the self compactability of concrete is concerned, or the high flowability of concrete is concerned, we are really looking at a trade off between these two opposing properties. One of them requires the paste phase or the liquid phase to be more deformable, whereas the other requires the same phase to be less deformable. So, it is basically a trade off. Building on that argument, we had discussed this slide, which talks about the possibility of blocking and the critical volume of sand required for blocking if we were doing an experiment as shown here, where in a small cylinder we are trying to push a piston which has a configuration like this, having holes of different diameters, and these diameters are related to the particle size that we have, and we had talked about a sudden change that is occurring here and a relatively sudden change which is occurring at around this value here. We had also talked about the history of the self compacting concrete briefly, and starting from about 1983-84 to about 1997 was an extensive amount of work done in Japan and in other countries, notably the Netherlands, where the emphasis was on developing high deformability, high flowability and self compacting concretes. On the other hand, there was a discussion and groups in the world working on high performance concrete interpreted slightly differently. They were working more on terms of increasing the strength of concrete. Now, coming to our discussion today, we will focus on self compacted concrete, that is SCC, and that is one of the examples of high flowability concretes. So, in this case, in addition to high flowability, the concrete should have self compactability, that is, it should not require external vibration in order to be compacted. So, we will cover basically the constituents and the test methods of this special concrete. As far as what SCC is, it really is a flowing concrete mix that does not require additional or external work for consolidation in terms of internal or form vibrators, and consolidates under its own weight. So, as we can see from the picture here on the right, the concrete more or less flows as if it were a fluid. Now, the advantages of working with this kind of concrete, that self compacting concrete, is that its highly fluid nature makes it eminently suitable for placing in difficult conditions, which could be sections with congested reinforcement, hazardous environment, and so on. So, at times the reinforcement arrangement or the arrangement of reinforcement is such that it makes it very difficult for concrete to be placed, for concrete to move through the reinforcing bars, and even if concrete can negotiate that gap, it is almost impossible to actually have a vibrator reach that area. Similarly, there could be hazardous environments where we would like to limit the amount of exposure to people, to human beings. We would like to have as few people working in that area as possible, and in these cases the use of self compacting concrete comes in very handy. As we said, that it can flow through tight sections comfortably as opposed to normal concrete, of course, provided the mix is designed appropriately. It has the right amount of segregation resistance. It minimizes hearing related damage induced by the vibration of concrete at the work site. The use of vibrators, whether it is internal vibrators or form vibrators, is one of the major sources of sound pollution at a construction site, and if we are able to get rid of that, we have a much more silent construction site. Indeed, the time required to place concrete in large sections is also greatly reduced, because the concrete virtually flows rapidly into the form that is being cast in. Here are examples where self compacting concrete would be eminently suitable. For example, if we look at this picture here, we can see that the reinforcement is so dense that it would be impossible for concrete to penetrate these small patches between the reinforcing bars, save the self compacting or a very highly deformable concrete. Only that concrete which literally flows like water can be poured into the formwork, and it can be expected that it will flow through these openings or gaps and set in a manner that a reinforced concrete designer would like it to. On the picture here is the anchorage of the 4A of the Akashi Kaikyo bridge, one of the major bridges in Japan, and I would like you to understand or study a little bit more on how the self compacting concrete was used in this large anchorage. As far as the ingredients of self compacting concrete are concerned, they are no different from the usual: cement, other cementitious materials, fly ash, blast furnace slag, microsilica, stone dust, aggregates which is fine and coarse, and admixtures which could be superplasticizers or viscosity modifiers. Now, we use or land up using a lot of these cementitious materials in self compacting concretes for the simple reason that we need to have a higher volume of paste, a higher powder content in the mix. This is something which we talked about last time, and we will look at it once again today. As far as cement is concerned, we can obviously use almost any type of cement. The typical cement content is no different from normal concrete. It is about 350 to 450 kgs a cubic meter. And higher cement content, obviously, if we use, we will land up with higher shrinkage and thermal stress issues. And therefore, even though we require a higher paste volume or a higher powder volume in the paste, it is not always advisable to use cement. We would rather use materials of similar fineness, but not having the hydration related issues in terms of heat and so on. And as we have stated, lesser cement content is possible by the use of these supplementary cementitious materials. As far as these materials are concerned, we could use fly ash, the blast furnace slag, or microsilica, preferably fly ash because of its spherical nature. Their use improves the workability and cohesiveness, reduces bleeding and segregation, improves durability and overall performance of the concrete. As far as the viscosity modifying admixtures are concerned, these are of various chemical nature and provide or correct or desired rheological profile to the self-compacting concrete. They improve the segregation resistance of the mix without loss of workability. They also help to reduce performance fluctuations due to variations in the material quality and the moisture in the aggregates. This helps us maintain a consistent quality as far as self-compacting concretes are concerned. Coming to aggregates, all sound aggregates meeting normal requirements are suitable. We must remember that with a material like concrete, it is very difficult to specify very special kinds of aggregates, whether it is fines aggregates or coarse aggregates, because concrete as a construction material is economical only if we use locally available material to the extent possible. The only factory made product used is cement, and that is where we can have some specification that okay, this cement and not that cement, this particular chemical composition and not that particular chemical composition, and so on. But if we become very choosy with respect to aggregates, that will push the cost of concrete beyond a certain point, and that would make concrete an uneconomical proposition. So, as far as possible, no matter how special the concrete becomes, the engineer always tries to use local material, and to that extent all sound aggregates meeting normal requirements are suitable for use in self-compacting concretes as well. These aggregates could be natural or crushed aggregates of any mineral composition, limestone, dolomite, quartz, basalt, whatever, except that the usual rules as far as alkali aggregate reaction will apply. We do not want to use reactive aggregates. As far as the maximum size of the aggregate is concerned, that is normally limited to about 20 mm, and aggregate shape should be round or cubical. Now, this is something which we need to be a little careful as far as its use in self-compacting concrete is concerned, because elongated aggregates do not produce satisfactory mixes due to an increased internal friction and their tendency for aggregate interlock. And that is something which we would like to really watch out against when we are talking in terms of self-compacting concretes. In normal concretes, because we use vibrators, we have the possibility or a chance to break aggregate interlocks with the vibrators, but in self-compacting concrete we cannot afford that. Similarly, we cannot afford aggregate interlock in equipment or in piping and so on. So, we must ensure that as far as aggregates are concerned, they are at least rounded or cubical in nature. Coming to superplasticizers, they are an essential component of self-compacting concrete because they help us reduce the water content. And as far as these admixtures are concerned, normal sulfonated melamine formaldehyde, naphthalene formaldehyde condensate, and polycarboxylic ether based superplasticizers are commonly used. Depending on the chemical composition of the cement, there may be issues relating to compatibility of a particular admixture with the cement and so on, and that is something which needs to be established from time to time as far as a construction site is concerned. As far as these admixtures are concerned, the water reduction achieved should be about 25% or more, so that the total content of water is restricted to about 160 to 180 liters per cubic meter. Anything more than that would make the demand on the powder content simply too high. Now, the mechanism of self compaction in self consolidating concrete is based on the large quantity of fines of the order of about 500 to 650 kgs a cubic meter, the use of high range water reducing superplasticizers in the range of more than 25% of water reduction, and viscosity modifying admixtures. So, it is these three principal factors or a combination of these factors which helps us obtain self compactability in concrete. So, when we are talking of a large amount of fines, we can imagine that if we are looking at 500 to 650 kgs per cubic meter of fines, this is not including the fine aggregate. This is really the fines in the sense of cement and particles which are of similar size. So, we cannot obviously have this amount of cement sitting in a concrete matrix. So, the cement content has to be restricted to about 350 to say 450, and therefore, perforce or by a requirement of self compactability, we need to have at least 200 to 250 kgs per cubic meter of either a supplementary cementitious material which will participate in secondary pozzolanic reactions or secondary hydrations, or a material which, even if it does not participate in that secondary hydration, contributes to increase the viscosity of the paste phase. Now, coming to self compacting concrete, all material passing through 0.125 mm sieve may be called fines, and that is how we were trying to define the fines in the previous slide. The total amount of fines required in a self compacting concrete depends upon its fineness, the water content, and so on. Pozzolanic materials will contribute to their strength, and their effect should also be considered on the mix design. Of course, we could use inert as well as reactive aggregate sometimes in fines, but with caution. Now, fly ash is one of the most commonly used supplementary cementitious materials and is a fine glass like powder recovered from flue gases created in a coal fired electric power generation or a thermal power plant. As far as India is concerned, we produce millions of tons of fly ash, but it is usually dumped in landfills. Fly ash as such is an inexpensive replacement for Portland cement to be used in concrete, while it actually improves the strength and segregation and also the ease of pumping in the concrete. Of course, it should be noted that not all fly ash can be used. It is not only the size and the reactivity and so on, but also the fact that the properties would depend on the coal which is used, the fineness, the burning temperature, and so on. So, if there is a lot of variation in the quality of coal being used in a thermal power plant, the quality of fly ash is also likely to vary. And this variation is one of the reasons why fly ash has not really become an absolute replacement for cement. Sometimes we get very good fly ash, and sometimes we do not get such good quality fly ash. And that is why, as far as specifications are concerned, as far as engineers are concerned, we cannot make a blanket statement that okay, we can use large volumes of fly ash in a given concrete. Of course, if an engineer is conscious of that, does periodic quality control, there is absolutely no reason why fly ash cannot be used. It is an ideal material for self compacting concretes. Now, if we look at the typical mixed proportions by weight of normal concrete and of self compacting concrete, these numbers here are those for a normal concrete, and these numbers are for a self compacting concrete. Now, if we look at these numbers, these are the proportions in mix 1, that is the normal concrete, and the self compacting concrete, and we are able to see the proportions by weight. Now, if this data was converted to a volumetric chart which says that air, water, powder or cement, sand and gravel, this here is the distribution as far as normal conventional air entrained concrete is concerned, and the picture below is that of a typical self compacting high performance concrete. Now, if we look at the numbers, in both cases we can assume that the air content is not really different, it is the same 2%, water is about the same. As far as powder or cement or fines is concerned, there is a marked difference. That is 10% in about 10% in conventional concrete, whereas in self compacting concrete it could be as high as about 18 to 20%. The sand is not really so much different, and this increase here is compensated by a corresponding decrease in the coarse aggregate percentage. So, in the end result, self compacting concretes have a larger paste volume compared to conventional volumes, and this is compensated or made up by the reduced volume of coarse aggregates, and that is something which we had talked about last time, and we had also seen this slide here which talks in terms of limiting the coarse aggregate content between 28 to 35% depending on the complexity of the formwork or complexity of the member in which self compacting concrete is to be cast. This ranking that is given here, rank 1, 2 and 3 for the aggregate content, is based on tests for self compactability, and the level of resistance at obstacles is varied for the tests in the 3 ranks. So, now when it comes to testing of self compacting concrete, that is really the second part of our discussion today. And now, let us talk about how we actually test self compacting concretes, which is different in a manner compared to conventional concretes. Now, conventional concretes we know we test in terms of workability and air content, maybe sometimes carry out bleeding tests or setting time and so on. And as far as workability is concerned, we do slump, compaction factor and so on. But when it comes to self compacting concretes or high flowability concretes, the material is beyond the classification range of a slump test. We need to have more specialized tests, and that is something what we are going to talk about. Some of the tests that we will talk about today are the slump flow, the V funnel, the L box, the U box, fill box and the J ring. Now, these tests give us an entirely different framework in which a self compacting concrete can be evaluated. We must remember that self compacting concrete has been developed only about 25-30 years ago, and therefore, a lot of these tests are still in some form of development or the other. Some of them have been standardized, and you can look up ASTM or European standards on that, but some of these tests are still evolving and would sooner or later become part of a standard quality control regime as far as quality assurance programs of self compacting concretes is concerned. It is not only self compacting concretes, but these tests can also be used to evaluate the workability of any other high flowability concrete. Of course, air content and so on can be tested in a manner which is similar to conventional concrete. Now, let us take a look at these tests one by one. Coming to the slump flow, the test aims at investigating flowing ability of the self compacting concrete and measures the spread, the diameter of the slump being a measure of that flowability, and indicates the free unrestricted deformability of the concrete. Recommended values of slump flow are in the range of 650 to 800 millimeters. What we must remember is that the standard slump cone measures 100 millimeters on the top, 200 millimeters here, and has a height of 300 millimeters. So, when we are talking of a slump flow of 650 to 800 millimeters, what we are really talking about is that this diameter here, which is what the concrete spreads into once the slump cone has been removed, this should be of the order of 650 to 800 millimeters or 600 to 850 millimeters. The original diameter here, as when it was contained in the slump cone, is about 200 millimeters. So, we are talking of a large spread of the concrete as the slump cone has been removed. When we are evaluating the concrete using the slump flow, we should also watch for aggregates having reached the edges. So, it should not happen that the concentration of aggregates in the periphery of the slump flow spread is different from the aggregate concentration in the center, and that is what is likely to happen if the concrete is segregation prone. If the concrete is segregation prone, the aggregate would not move with the mortar towards the periphery. As a corollary to the slump flow test, we also sometimes use a flow time, which is sometimes called the T500 test. And now, this T500 refers to the time it takes for a concrete to achieve or reach a diameter of 500 millimeters, and the typical time could be in the range of 2 to 5 seconds. So, as the slump cone measuring 200 millimeters in diameter is lifted, the concrete spreads in all directions, and we look at the time that it takes for the concrete to reach a diameter of 500 millimeters, and this time is called the T500. Depending on the kind of viscosity that we have as far as the mortar is concerned, it is possible that for the same slump flow, which is the final diameter that the concrete really achieves, the T500 times could be different, and obviously the T500 would be higher for a concrete which is more viscous, and concrete being more viscous really means that the mortar phase has a higher viscosity. So, even though we are not measuring viscosity directly, parameters such as the T500 help us to determine and compare the viscosity of two concretes which have the same or different slump flows or that final spreads. Now, if we look at the slump flow test once again, we would realize what the import of the free unrestricted deformability is. The concrete in the slump cone, as it flows out, is unencumbered. It flows out freely without any encumbrance, without any obstacle or obstruction to its flow, and that is not something which we have as far as most reinforced concrete structures is concerned. In most cases, the concrete is expected to negotiate reinforcing bars, and that is something which the slump flow itself does not measure. So, most of our tests beyond this point have this parameter added into the testing regime. Now, if we come to the V funnel test, the test gives us the time for a certain volume of concrete to pass through a narrow opening. It gives an indication of the filling ability, provided that no blocking and or segregation occur. Concrete samples would depend upon the size of the V funnel. It could be about 12 to 14 liters, and the time would vary between 6 and 12 seconds. So, if we have concrete filled in this funnel, which measures about say 500 millimeters on the top, has a width of about 75 millimeters here, and a height of 450 millimeters with a constricted region here of about 150 millimeters, what we expect is that the concrete filled in this portion here, there is a lid which when opened allows the concrete to flow through this, and the time that it takes for the concrete to flow through is the V funnel time. Now, once the concrete is flowing from a larger cross sectional area to a smaller cross sectional area here, the possibilities of aggregate interlock can be easily checked, and that is something which the slump flow simply cannot do. The slump flow therefore is the measure of the unrestricted deformability, whereas a test such as the V funnel helps us evaluate the concrete from the point of view of aggregate interlock and so on. As far as the time is concerned, when do we say that all the concrete has actually passed through the funnel? One of the methods that can be used as a basis or as a guideline can be, once the concrete moves through this funnel, if we are watching from the top, we should be able to see the light at the end of the funnel, and this funnel has a diameter of about, or a square is about 185 or 80 mm, and that is something which would help us. Now, coming to the third test that we need to talk about, and that is the L box. Now, this test here means or has an L box, that is, there is a box here which is, let us say, A, and another portion here which is, let us say, B, and we fill the concrete in A. There is this gate which is closed, and once we lift this gate, the concrete from the block A flows into block B. Now, this flow from block A to block B is restricted by the presence of these pipes or reinforcing bars or any such arrangement that we may choose to use. Some of the standards have standardized the kind of obstruction that can be used in the form of pipes of different diameters or in the form of reinforcing bars of different diameters, in a manner that the space here is divided into different open spaces. So, the kind of obstruction that we use here is somehow related or somewhat related to the kind of reinforcement in an actual structure which the concrete is expected to negotiate. So, of course, here also we have the possibility of an aggregate interlock occurring behind the reinforcing bars, which would prevent the concrete from block A flowing into block B. So, the kind of measures that we need to take, or the kind of measure that would be used as far as testing the L block is concerned, it is largely the difference in this height at these two places. So, H1 and H2, and then there is this delta H. So, if the concrete was to behave as a real fluid, then we would not expect any difference in the height over this length that the concrete is flowing. But since the concrete at the end of it is not really a fluid, there will be a certain amount of difference in the heights at these two places, and that is the difference that we want to monitor and measure as the output from this test, which is called the L box test. As I explained before, that this is what is given in the text here. The method is useful to investigate the possibility of self-compacting concretes, the possibility being the ability of the concrete to negotiate the simulated reinforcing bars, and it measures the reached height of fresh SCC after passing through the specified gaps of steel bars and flowing within a defined flow distance, which was shown to be about 700 millimeters in the previous slide. And with this height reached, the passing or blocking behavior of the self-compacting concrete can be estimated, and two types of gate can be used, one with 3 smooth bars or 2 smooth bars. The gaps would be different depending on the kind of diameters of the bars that we use and so on, and we can have standards which would help us evaluate a concrete from this point of view, that is from the point of view of an L box test, which is using the ratio of the heights at the beginning and end of the flow. So, like we have always stated in this discussion in different lectures as far as this module is concerned, test methods are always such that they would yield a value. Any test method, any test would yield a value, and a specification is something which the engineer has to say or state that okay, if we carry out this test for this application, this is the value which is acceptable. So, we can in this case, for example, have different tests as far as self compacting concretes are concerned, and the engineer can lay down different specifications. As far as the L box test is concerned, I want a concrete which has a ratio of the two heights to be, let us say, 0.9. As far as the funnel test is concerned, I want a concrete which should not have a time of flow greater than, say, 10 seconds. It should not have a slump flow less than 55 centimeters or 550 millimeters and so on. So, this is the basic concept in terms of testing of self compacting concretes. Continuing with the tests, let us look at the U box test. As the name suggests, talks about the flow of concrete in a U shaped box. So, concrete is filled on one end of a U box, closed initially with a gate, and this gate has an obstacle which again has simulated reinforcing bars. And once the gate is opened, the concrete flows from one end to the other, and we can always talk in terms of this height or the difference in these two heights. And again, if the concrete was a fluid or a liquid in that sense, then we do not expect any difference in the heights in the two sides of the U. Again, because concrete is not a true liquid in that sense, we will expect a certain amount of difference, and that difference would be the measure of the self compactability of the concrete. The smaller this difference between the two sides, the more self compactable the concrete can be stated to be. Again, this gate or this obstruction that we design or use as far as this test is concerned can be modified or chosen to be in a manner that represents the kind of reinforcement that we use. Coming to the fill box test, which is a slight variation of the test that we used earlier. This test here deals with the concrete's ability to fill a box once the concrete is placed in this end of the box, and these pipes here represent the actual reinforcing bars or the reinforcement in a reinforced concrete structure. So, depending on the complexity of the reinforcement that we are emphasizing in a particular application, we can change the diameter and the spacing of these bars and have the concrete fill this box. Normal concretes, as we can imagine, will not be able to more or less negotiate the gaps between the simulated reinforcement almost at all. It is only after a certain amount of self compactability or higher level of deformability that is achieved will we get some semblance of a horizontal surface, which is what we finally want in a truly self compacting concrete. Last of all, in this series of tests that we are talking about, let us talk a little bit about the J-ring. Now, the J-ring test aims at investigating both the filling ability and the passing ability at the same time, and indicates the restricted deformability due to blocking effect of reinforcing bars. In a manner of speaking, the J-ring is a combination of the slump float kind of test with the added complication that the concrete is required to flow through this added cylindrical contraption which has these reinforcing bars and gaps in the bars. So, the concrete is placed in the usual manner in a slump cone with this contraption on the outside, the cone is removed and then concrete is allowed to flow through this contraption. And as it flows through, it is not the free unrestricted flow as we would expect in the case of normal slump flow, but the concrete is flowing now through obstacles, and the measure could be in terms of again the flow that we achieve or the difference in heights inside and outside this barrier and so on. A variation of the T500 time that we talked about when we were talking about a corollary to the slump flow is the T500J. The T500J is the time that it takes for the concrete to achieve a diameter of 500 millimeters when tested with a J ring. T500 was the time that it took for the concrete to reach a diameter of 500 without any restriction or without any obstacle to its deformation. So, this J here is the added suffix and helps us find out the viscosity of the concrete with the modified slump flow, that is using a J ring. These pictures here show another representation or view of the J ring test. There is another test which we have not talked about or we had not listed in this discussion, and that is a test which involves having the concrete pass through a large U tube where there is a substantial amount of distance involved here, and we place the concrete here, expect the concrete to flow all this distance and rise in this tube here. So, it is a variation of the U tube test that we talked about, except that the concrete is just not flowing from one leg of the U to the other, but it is passing through a reasonably long distance. Now, as this concrete goes through this distance, we can always have innovations which would create obstacles in the path of the flow and still expect the concrete to negotiate the barriers that we put in place. This kind of a test, because of its size, can also help us evaluate properties of concrete at this end of the flow, that is the end where the concrete is being poured, and this end here where the concrete is reaching at the end of the flow. So, we can take core specimens at the end of the whole thing, at the end of the hardening and the strength development and so on, and we can try to find out properties such as strength, maybe even particle size distribution, of coarse aggregates and so on using these cores, and to establish at the end of it conclusively that yes, the concrete at this end and this end is really the same, and it did not go through any segregation and so on while it was negotiating this whole path. Now, before we close, I would like to thank my erstwhile colleagues in Kajima Corporation, especially friends like Mr. Motohashi, Sakata and Takada, for the insight they helped me get into this fascinating subject of high flowability self-compacting concretes. Now, before we close, of course, as usual, we will have a series of items which we could look into a little bit more closely to get better understanding of self-compacting concretes. We could make a list of case studies where self-compacting concrete has been used. We could study from that list of projects, we could try to understand how was the self-compactability achieved in these cases. We have talked about different routes, we have talked about increasing the powder content, use of chemical admixtures, that is superplasticizers, or the use of viscosity modifiers. So, these are some of the routes that we talked about in theory. Now, once we look at the actual concrete mixes being used in different projects where self compacting concrete was used, it would be possible for you to understand which of the routes was taken to achieve self compactability in these cases. We have talked about some tests in our discussion today to give you insight into the different variations that have been proposed and are being used in different standards to evaluate the self compactability of concrete. There are several other tests which we of course had not had the time to cover, and we could try to make a list of other tests that have been suggested in literature for the self compactability of concrete. Now, as a corollary to this question, we could have a list of standards which address the tests that we use today, the slump flow, the J ring, the U tube, and so on. There are variations in even the slump flow test, and I would like you to examine some of the standards which describe the slump flow test. Learn more about these tests as we have discussed. Seeing is believing. There are several videos and movies available on the internet which you could take a look and see how these tests are actually carried out. Once you see these tests being actually carried out, that will give you a much better understanding on what we are talking about, the deformability, how the concrete flows as far as the slump flow is concerned, how that high flowing concretes are placed in more congested formworks, and so on. With this, we come to an end of the discussion today on self compacting concretes. Thank you.